Welcome to Mrs. Mahoney's Unit 2, Podcast 2. This is all about energy, and more specifically, the energy involved when we have a change of state. So when I'm talking change of state, remember our three common states of matter: solid, liquid, gas. I know there's plasma. We're not talking about plasma in chemistry. I can't bring a star into the classroom or a jar of lightning, so we won't be dealing with plasma. Let's just look at what we're most comfortable with: water. So we have our solid, liquid, gas, commonly known as ice, water, steam. But really, don't forget, this is H2O. 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 It's still just a compound of water. Difference where the molecules are. Packed really, really tight together. More room between them. They can flow. Lots of space. And therefore the molecules can really move around. That's why you can't see them. It's a gas. So if we change from one to another, what are we doing? This is called fusion. More commonly melting. Happens at the melting point. Vaporization, liquid to a gas, happens at the boiling point. We also know it as evaporation or boiling. Go backwards. Condensation happens also at the boiling point. Water to ice. Solidification, commonly known as freezing. Physical changes. What's the difference? Where the molecules are in relationship to each other. A couple ways we can make this happen. Add a lot of pressure and a really, really low temperature, and we get ice. High temperature, not a lot of pressure pushing them together, then we're going to get a gas. We're not going to worry about the pressure right now. We're going to worry about the temperature and the energy needed to go from one to another. So let's start with our first one, evaporation. Let's look at just going liquid to a gas. So we'll start with evaporation. I have a liquid going to a gas. Now we're going to start seeing more of these as an equation. Read them just like you read a sentence, left to right. So on the left side is what you start with, the arrow almost like an equal, or what it's going to turn into. So I have a liquid turning into a gas. How does that happen? Because I add some heat. Heat is energy. Means the same thing. We measure it in joules, and we abbreviate it with a J. So if you say joules, or how many joules, or how much heat, or how much energy, this is what it's asking for. The V is telling me it's for vaporization. That it's looking, vaporization is when I'm going from a liquid to a gas, gas to a liquid. Look at where this energy is in relationship to the arrow. I'm adding it to the liquid, and then it becomes a gas. So it's an endothermic reaction. Or actually, it's not even really a chemical reaction, it's just an endothermic change, because I had to add heat or energy to the system. It's a positive sign because it was added, it was taken in. Look at the reverse. What is condensation? Gas going to a liquid. Look at where the heat is in relationship to the arrow. It's given off. It's being released. If something is losing energy, releasing energy, it's exothermic. Think of an explosion, except for, again, we're not talking chemical changes. We're just looking at a physical change, but it still has a negative sign. Heat is given off. It's being released. How about our other state change? Solid to liquid. If I have freezing, freezing is going from a liquid to a solid. So look at this. It's not always going to be in the same order. So is this endothermic or exothermic? Look at where the heat is in relationship to the arrow. It's exothermic because it's been given off. It's released. We call this, notice the F, that's for the heat of fusion. So if I'm melting, it's a fusion. If I'm boiling, liquid to gas, gas to liquid, it's V, vaporization. This is why when crops are getting close to freezing, they actually turn the water on the fruit, the oranges, which seems really weird. Why are they trying to freeze the fruit? Because when water freezes, it releases heat, and that heat is what's going to keep the fruit from freezing. Look at the opposite direction. Melting to solid. Well, think, if you want to melt ice, what do you have to do? Add heat. That's what I'm telling you. Solid plus some heat, and you're going to get a liquid. Endothermic. Add heat, It's going to be endothermic. Look at my signs here, guys. This is backwards. Hope you caught that. This was something that didn't get changed. Exothermic should be minus. Endothermic is going to be a positive. So make sure you change that and you have the right one. That was my slide, but I'm not going to start all over. Okay, let's look at this second way, another way of looking at this. This is just called like a heating curve. This is where you need to get comfortable in reading these. You have this in your notes. Let's add just some other information to it that I think you need to know. But first, what are we saying? Look at this as the temperature goes up, it's on this side, and we're adding energy. So we're always adding energy. So right here, until I get to this, it's heating, heating, heating. Then right here at this point, something's going to start happening. Look at what happens. Solid becomes a liquid. Then we get just liquid, heat, heat, heat. And then a liquid becomes a gas. And then we have just gas. So where this happens, right here, this point A, this is my melting point. And I would be adding some more writing on your own that's in your packet. You need to label some of these things. Point B then, look what's happening, liquid to a gas. This is the boiling point. So let's talk in terms of energy. So look what's happening. It's heating, heating, heating. Those molecules are going faster, faster, faster. Heating, heating, heating. Molecules going faster, faster. So whenever you have a diagonal line, what we are doing is getting a change in kinetic energy. Kinetic energy means movement. Those molecules are heating up and moving faster, faster, faster. This also has kinetic energy, Ke, abbreviating Ke. So it's on the hot plate, getting hotter, they're moving. But look at what happens here. It's still on the hot plate, but it's not changing temperature. Not changing temperature. So we still have an energy change, but it's a different kind of energy. So wherever you see a flat line, what's happening? We get a change in potential energy. And what it's doing is taking that energy to change it from a liquid or to a gas, or changing it from a solid to a liquid. So where you get potential energy, you get a change of state. It's either going to be melting or freezing. It's going to either be boiling or evaporating, vaporization, or condensing. We can read these forward, or we can look at it in reverse. One thing when we're looking at this, look at all these directions. Solid to a liquid. When I read it in the forward direction, this is endothermic. When I read it in reverse, all of those are exothermic. So that's where I can say, oh, okay, so I'm going from a solid to a liquid. Solid to a liquid, melting, endothermic. Liquid to a gas, boiling, endothermic. Go in the reverse, condensation, exothermic. In reverse, exothermic. Okay, let's have some questions on that. So look at right there, I've added what I've written all over, change of state, change in potential. So make sure you've got those labeled. Change in same state, change in temperature, that's where we get our kinetic energies. Know where those two differences are. Okay, let's answer some of these quick questions. Where does melting begin? Look on your graph. Solid, solid, solid. Solid, solid, solid. Where is it becoming? Point C. Ignore the random drawings. Where's condensation starting? Point F. From point D to C, heat is doing what? What I'm looking for here, is it being absorbed or is it being released? What's happening from D to C? It's being released. And then what type of energy is involved during a phase change? This is a phase change because I'm changing phases. Liquid to a gas, phase change. Solid to liquid, phase change. What kind of energy did we say? It was potential energy, which we could abbreviate, you see, as your potential energy, PE. So let's sum it up. As we were looking there, we've got our changes of energy and vaporization, and we're looking at it. You have a certain amount of energy. We're going to calculate those when you come in tomorrow. We're going to just look at how we calculate some of those. Energy out. So energy in, endothermic. Energy out, exothermic. But look at the numbers. The numbers are the same. The amount of energy it takes is the same. The only difference, if it was energy out, I would say it's negative because it's being released. It's energy in, it's positive because it's being absorbed, it's being taken in. We're going to do some sample calculations of the energy required. We talked about that phase change. It's taking energy. How much energy? Here's my formula that I want to use. Q equals G is grams times heat. Q is energy. Don't ask me why. It's not E. E, we have enthalpy and entropy. We just start doing some random ones. Q is energy or heat. It's the heat, or it's just the same thing as the energy. Depends on two things. How much do you have? G, grams. Then each substance has a specific heat of vaporization or heat of fusion involved. The higher this heat, the more energy it's going to take. If I have a really, really low heat of fusion, it doesn't take very much energy. If I have a really, really high heat of fusion, it's going to take more energy. So it's just a formula we're going to plug in and chug out some answers. Remember, if it's a negative, it's exothermic. Positive means endothermic. So look at what we're doing. We're condensing. That's straight. 5,000 milligrams of water. Okay, Q, I know I need grams. And this is where I have to say, okay, condensing. Am I vaporizing or am I fusion? That's vaporization. So I need to calculate my Q, but it needs to be in grams. Man, this is when we have to do some more conversions. Dimensional analysis. Milligrams, I need to go to grams. 1,000 milligrams, 1 gram, means you're going to be dividing. So what do I have? I have just 5, and I'm keeping all my sig figs, that's a 0, 5 grams of water. So Q is just equal to your 5 grams times the heat, and we look, it's vaporization that I'm using, so I'm going to plug in the 2,264, and then you're going to just plug it in the calculator, 5, and when you're plugging those in, you don't have to worry about typing in all those zeros. That's just a significant issues. But look what I have, 4 significant figures, 5, I'm going to put 4 in my answer, so I can have 11,320 joules, label it a J. That's how much energy I need. But then I'm looking and condensing. Wait, that's releasing. My 100% proper answer, it needs to be a negative sign. Exothermic is releasing it, so it has to have a negative. Next problem, key things. I first notice it's in kilojoules. Then I'm looking vaporization. So again, I'm having to look at the vaporization. And they give me this time that heat. The reason it's different, this isn't water. These heat of vaporizations up here only for water. So look at this one. It takes a lot less energy. It's that many joules per gram. Water is 2,264 joules per gram. It takes a lot more energy to vaporize than it does. It takes a lot less energy to vaporize this compound than my compound of water. First thing, it has to be in kilojoules. I have kilojoules, it has to be in joules, excuse me. So I know kilo is 1,000. So there's 1,000 joules in 1 kilojoule. And I'm going to shift, because I don't want to lose my sig fig, I'm going to shift to scientific notation. So that's how many joules times 10 to the 5th. So now I'm going to plug in what I know. That's my heat. That's my Q times 10 to the 5th. I'm looking for that mass times 21. So then I'm just dividing 3 significant figures. It's going to take 23,800 grams of sample. That's a large sample, but that's a lot of energy, so that number makes sense to me. It's okay. Okay, the top of page 6, there's just one more question, number 3. I'm not going to answer it. I want you reading it and answering it, and we'll talk about it in class tomorrow. See you tomorrow.